This is the video on gas laws. So remember, in these videos, there will be two codes. There will be one, a written code on the screen, and the other code will be a verbal code said by myself. Each code will be 3 numbers. You will need the codes in order to move on with the homework assignment. So remember, when taking notes, the important things are in green. So the rest of it is just good information, just to make a good coherent thought. But if you're taking notes, what's in green should be in your notebook. So this is the weekly review video, the written code. I would recommend writing this down somewhere. All right, so the question is, what are the 4 variables in the gas laws? So let's just take a look at what gas laws are. Well, they're a mathematical relationship between different gas variables. So the variables that are in the gas laws will temperature, which we measure in Kelvin, pressure, which is measured in atmosphere, volume, which is measured in liters, and moles, which is measured in moles. So before we do the gas laws, we need to look at the different temperature scales. So Fahrenheit, Celsius, and Kelvin. So if you're from America, you're probably used to the Fahrenheit scale. Celsius, most other countries in the world use Celsius, and Kelvin is more of a scientific one. So you can see that over there. And the difference is what constitutes zero. So like Celsius and Kelvin, they use the same, the degrees are the same distance apart, right? So like if a temperature goes up 1 degree Celsius, it goes up 1 degree Kelvin, but the difference is where zero is. So 0 Celsius is when water freezes, but 0 Kelvin is absolute zero. That's when there's no motion within the atoms or molecules. Now, when we're using the gas laws, we need to use Kelvin temperatures in all the gas laws, otherwise the formulas don't work. Now, to convert from Celsius temperature to Kelvin, you need to add 273. So to get Kelvin, degrees Celsius plus 273. So an example would be what Kelvin temperature is equal to 25 degrees Celsius, 25 plus 273, 298 Kelvin. All right. Now, when we're talking about pressure, pressure is force per unit area exerted by air. What causes pressure is collisions of gas particles cause pressure. Now, there are many units for pressure: atmospheric pressure, pascals, torr, millimeters of mercury, psi. You're probably used to psi the most, like if you're filling up a car tire or a bike tire, that's what's used. But the unit for pressure that we'll be using in this class will be the atmospheric pressure, ATM. You can use any of them. That's just going to change the constant, the constant, and we'll get to that later. But we're going to be using atmospheric pressure. So atmospheric pressure presses in all conditions. As altitude increases, the air pressure decreases. So let's just go into the laws. So Boyle's law states that pressure and volume are inversely related if temperature is constant. That means if one goes up, the other goes down. If one goes down, the other goes up. So that's the equation over there. So this is a problem that you can have. So let's just take a look at the problem and how to do these. So follow these steps. First, you convert temperature from Celsius to Kelvin by adding 273. We don't need to worry about that because we don't have any temperature in this equation. Just fill in what you know, solve for the unknown. So this is a problem that you can have with Boyle's law. A balloon with a volume of 2 liters is filled with a gas of 3 atmospheres. If the pressure is reduced to 2 atmospheres, what would the new volume of the balloon be? So the answer is going to be 3 liters, but here's how I got this. First, I fill in everything that I know. I know the original pressure is 3, the original volume is 2 liters, the new pressure is 2. Well, what happens to the volume? Plug everything that I know in, and I get 3 liters. So now Charles' law states that volume and temperature are directly related if pressure is constant. So let's just take a look at a problem that we can do with Charles' law. So now we do have that convert temperature from Celsius to Kelvin by adding 273, fill in what you know, solve for the unknown. So this is a problem. A 3-liter balloon is at a temperature of 25 degrees Celsius. What is the new volume of the balloon if the temperature decreases to 18 degrees Celsius? So the answer is 2.93 liters. But here's how I got this. Now notice for the original temperature, what I had to do was I added 273 to 25. And to get the final temperature, I added 273 to 18. So then I plug in everything that I know. Let me move this video screen so you can see. What you need to do is you need to cross multiply, right? This is how you can solve these kind of problems. 3 times 291 divided by 298 will get you 2.93 liters. So these are how you solve these problems. Really easy with that cross multiplication. So now let's get to Gay-Lussac's law. Now this law states that pressure and temperature are directly related if the volume is constant. So here's a problem that we can have with Gay-Lussac's law. So same steps. We add 273 to Celsius, fill in what you know, solve for the unknown. So here's a problem. A cylinder contains a gas of 6 atmospheres and 27 degrees Celsius. What would the pressure of the gas be if the gas was heated to 350 Kelvin? So the answer is going to be 7 atmospheres, but here's how we get that. We plug in everything that we know. Now, one thing that I want you to know, this is kind of a tricky problem because I have Celsius, right? I had to add 273 to 27 degrees to get the original temperature, 300 Kelvin, but my final temperature was already in Kelvin, so I didn't have to add anything to that. So just make sure you take a look at those units. Now I fill in everything that I know and I solve for the unknown. So cross multiply. 6 times 350 divided by 300 is 7. So that's how you solve a Gay-Lussac's problem. So let's talk about standard temperature and pressure. So standard temperature and pressure refers to the nominal conditions in the atmosphere at sea level. So STP is 273 Kelvin and 1 atmosphere. At STP, 1 mole of any gas occupies 22.4 liters. So you can see this little graphic over here. It doesn't matter whether it's a lighter gas like helium or a heavier gas like chlorine. If I have 1 mole of any gas at STP, which is 273 Kelvin and 1 atmosphere, that gas will occupy 22.4 liters. So now that we know that, we can go into the ideal gas law, and that describes the behavior of a gas in terms of pressure, volume, number of moles, and temperature. Now we're not keeping anything constant. We're just seeing how they all react. Now, there's one thing in this that you can see, right? R. R is the ideal gas constant. Now, because we're using atmospheres, this is our ideal constant that we're going to use. 0.0821 liters, liter atmospheres per mole Kelvin. Now, the reason why that unit looks kind of weird is because when you multiply all this out, we need to make sure, number one, the math works out, and the units, all the units cancel out except the one that we're looking for. So if you look over here, there's also all these equations. So this is just the ideal gas law rearranged to give you the to solve for the unknown, right? So number of moles, volume, pressure, and temperature. So at this time, I'll go ahead and I'll give you the verbal code. The verbal code is 463. I say that again. The verbal code is 463. All right, so this is an ideal gas law problem. So convert temperature from Celsius to Kelvin by adding 273. The one additional step that we have to have is use 0.0821 liter atmospheres moles per Kelvin as R. Fill in what you know. Solve for the unknown. So problem, how many moles of gas are there if 25 liters of gas exert a pressure of 0.5 atmospheres at 300 Kelvin, 0.5 moles? That's going to be the answer. How did I get that? Well, I just plug in everything that I know and solve for the unknown. 0.5 times 25 divided by 0.821 divided by 300 gets you 0.5 moles. So we did a simulation where we tested those the three gas laws that showed how all of them react by keeping one constant, and then we did some gas law problems. So as a final thought, remember there's just too much unknown in the universe to take a break from learning. Get out there and question everything.